Hello everyone, I am Tanmay Das, and on behalf of Team NeuroSync Labs, I would be presenting our project Adaptive Motor Synchronization and Coaching System, also the NeuroGlove. Neuromotor and sensory processing disorders affect millions of children and adults worldwide. Conditions such as dyspraxia, developmental coordination disorder or DCD, sensory processing disorder, cerebral palsy and related motor control disorders can significantly impact a person's ability to perform even simple daily activities. Studies estimate that developmental coordination disorder alone affects nearly 5 to 6% of school-aged children, while many adults continue experiencing long-term motor condition difficulties throughout their life. Individuals facing these conditions often struggle with delayed movement initiation, unstable hand movement, excessive or uneven grip force, difficulty in coordinating the intentional actions, tremor like instability, and fragmented motor execution during routine tasks such as maybe writing, holding objects, reaching or maybe catching an object such as a ball. One of the major challenges is that many existing rehabilitation systems are either mostly based on therapies, and they could be either expensive, they could be either non-portable, clinically restricted, or incapable of providing real-time adaptive behavioral feedback during the natural everyday movement. To help address this problem, we developed the Adaptive Motor Synchronization and Coaching System, also called the NeuroGlove, an AI-assisted wearable rehabilitation and behavioral analysis framework designed to monitor the human motor behavior in real time and provide intelligent assistive feedback during movement execution. Our prototype integrates multiple sensing and processing modules into a single wearable system. The system consists of an ESP32 microcontroller for real-time processing and wireless communication, an MPU 6050 for which is the inertial motion sensor for acceleration and orientation tracking. It also has a force-sensitive resistor, or the FSR for grip force monitoring, APDS 9960 proximity and gesture sensor for contextual interaction analysis, BMP environmental sensing module for environmental state awareness, OLED display for life system visualization, SD card logging for behavioral dataset collection, and Bluetooth enabled mobile assistive interface, and a deep learning based temporal behavioral inference pipeline. What the MPU 6050 does here is it continuously tracks movement smoothness, acceleration progress, directional stability, and the motion continuity. The FSR analyzes the grip force buildup, force variability, and pressure irregularities during object interaction. The APDS 9960 assists in the contextual interaction estimation by analyzing the hand proximity, interaction timing, and movement intent progression. The BMP environmental module helps the system differentiate between instability caused by neurological tremor-like behavior and external environmental conditions such as maybe shivering during cold climatic conditions. This reduces the false positive instability detection by incorporating environmental context into. The NeuroGlove architecture is designed as a multimodal behavioral analysis framework combining signal processing, sensor fusion, classical machine learning, temporal deep learning, adaptive personalization, and probabilistic behavioral inference for real-time neuromotor rehabilitation assistance. Basically, now I have powered the NeuroGlove on. The NeuroGlove is connected to the device via Bluetooth connection. After launching the NeuroGlove interface, the system begins an initial behavioral calibration phase. During this phase, the wearable records baseline movement characteristics including motion smoothness, grip force behavior, acceleration consistency, and natural locomotor motion patterns. These preliminary readings help the temporal behavioral model establish a personalized movement profile for the user. Now I will turn the NeuroGlove interface on and show you.
unstable.
Now the system has calibrated the user's initial movement behavior and can begin monitoring for hesitation patterns, instability buildup, and abnormal force modulation during intentional actions. Focus on the detection of delayed hand movements. For example, now I am walking, excuse me, and so my hands are also moving. However, the system does not generate assistive feedback because these movements are identified as low priority background locomotor patterns. The temporal interface engine understands that casual arm swings during walking lack intentional action buildup, directional stabilization, and sustained movement continuity. Now suppose I attempt to catch a ball.
Action. Action.
So before the actual action occurs, the hand begins exhibiting preparatory destabilization, directional motion buildup, acceleration progression, and intentional reaching behavior. However, during delayed motor initiation, the movement may briefly stall or fragment before the final action fully executes. The deep learning model continuously analyzes these evolving pre-action signatures. And when recurring hesitation patterns are detected during the initiation phase itself, the system predicts probable movement delay and generates anticipatory assistive feedback before the delayed action fully develops. So now, for example, while holding a sheet of paper, the force that is required is naturally very small, of course. If the user suddenly applies excessive and unstable grip pressure while interacting with a lightweight object, the behavioral model, which is initiated by the FSR, interprets this as abnormal grip force modulation. However, while holding a heavier object, such as a bottle, the same force value may be completely appropriate. The system therefore does not rely on fixed universal force thresholds alone. Instead, the AI combines grip force progression, temporal motion behavior, hand stabilization dynamics, motion interaction timing, motion trajectory, and proximity-based contextual estimation, which is to probabilistically determine whether the applied grip force is behaviorally appropriate for the current context or not. Now I will show you the demo for the same while you holding a bottle of water and while grabbing a piece of paper with approximately equivalent amount of forces. Now when I'm holding this bottle over this much surface area, the pressure that is applied is correct for this. It's not abnormal. But on the other hand, when I will grab this piece of paper with too much force, the interface gives us the instruction that we need to reduce the pressure. In addition to the delayed movement initiation and grip force dysregulation, NeuroGlove is also capable of analyzing tremor-like instability patterns and fragmented motion behavior. Under normal conditions, intentional hand movement generally follows a smooth trajectory, stable acceleration progression, and controlled directional continuity. However, during tremor-associated or unstable motion states, the hand may exhibit rapid micro-oscillations, corrective shaking, inconsistent acceleration, and fragmented movement progression. The temporal behavioral model continuously evaluates these instability signatures across synchronized IMU motion streams. For example, while the user is performing a reaching action, the system monitors oscillation frequency, acceleration irregularity, motion fragmentation, and stabilization inconsistency. Now, if the instability exceeds the user's learned behavioral baseline, the wearable generates adaptive assistive feedback. I will show this with the help of an example. For example, if I'm holding a pen and my hands are shaking.
Please slow down and stabilize the movement. Please slow down and stabilize the movement.
So this is how the NeuroGlove device detects the trembling hand movements. Just designed to monitor the movement, but to understand the behavioral patterns underlying human motor execution. By combining multimodal sensing, adaptive behavioral analysis, machine learning, and temporal deep learning frameworks, our objective is to move towards a future where wearable rehabilitation systems can provide real-time intelligent assistance during everyday life. In the future, systems like NeuroGlove could contribute towards personalized rehabilitation, adaptive motor coaching, early instability prediction, and accessible assistive technology for individuals facing motor and sensory processing challenges. Our project aligns with SDG 3, which is Good Health and Well-being, SDG 9, Industry, Innovation and Infrastructure, and SDG 10, which is Reduced Inequalities. Thank you.